Basic definitions of maximum and minimum values. Hello, everyone. Today, we are beginning our exploration of a very important topic in calculus, specifically within the section known as the application of derivatives. In this area of study, we frequently encounter the need to identify the absolute highest and lowest points that a function reaches over a certain range. In mathematical terms, these peak and valley points are formally referred to as the maximum and minimum values of the function. Now, before we dive into the actual calculations and the specific techniques of using derivatives to locate these points, it is absolutely essential that we first establish a clear and precise understanding of these basic definitions. Having this conceptual foundation will be crucial as we move forward into the more technical parts of the lesson. Maximum value of a function. Now that we have introduced the general idea of finding the highest and lowest points of a function, let's dive into the formal definition of the maximum value. First, let's set the stage. Suppose we have a function, f of x, which is defined over a specific range or interval, which we will call interval I. In simple terms, we say that the function f has a maximum value in this interval I if there is one specific point, which we'll call c, where the function's value is greater than the values at every other point within that same interval. To express this more formally, a function f has a maximum value in interval I if there exists a point c belonging to I, such that f of c is greater than f of x for all x in I, where x is not equal to c essentially. This means that at point c, the function reaches its absolute peak for that specific section of the graph. Now, I want you to pay close attention to the terminology here, as this is where many students often get confused. The actual output, or the height of the function, f of c, is what we call the maximum value of the function in interval I. However, the input value, c, is referred to as the point of maximum value. It is crucial to distinguish between the value and the point now, because as we will see in our later examples and common mistakes section, mixing these two up is a very frequent error. Once you are comfortable with this, we will move on to the definition of the minimum value. Minimum value of a function. Now that we have discussed maximum values, let us move on to the opposite concept. Similarly, we are now looking for the lowest point of a function. We say that a function, f, has a minimum value in a given interval I if there is a specific point, c, within that interval where the function's value is smaller than the values at all other points in that same interval. To state this more formally, a function f has a minimum value in interval I if there exists a point c belonging to I such that the function of c is less than the function of x for all x in interval I, where x is not equal to c. It is very important to distinguish between the following two terms to avoid confusion later on. First, the resulting value, f of c, is called the minimum value of the function in interval I. Secondly, the specific input value, c, is called the point of minimum value. Extreme values and extreme points. Now that we have established the individual definitions for maximum and minimum values, let's move to slide 4. To make our mathematical language more efficient and concise, mathematicians use a collective term to refer to both maximums and minimums simultaneously. First, let's look at the term extreme value. An extreme value is simply an umbrella term. It refers to any value that is either a maximum or a minimum. So, whether you are dealing with the highest point or the lowest point of a function, you are dealing with an extreme value. Similarly, we have the extreme point. This is the specific point, c, at which that extreme value occurs. Just as we distinguished between the value and the point in our previous slides, the extreme point is the input coordinate that leads us to the extreme value. Understanding these collective terms is important because, as we move into the next slide, we will apply these concepts to a real-world scenario involving projectile motion. Real-world example, projectile motion. Now that we have established the formal definitions of maximum and minimum values, let us apply these concepts to a practical, real-world scenario to see how they work in action. Imagine a ball is thrown vertically upward. We can represent its height, denoted as h in meters, at any given time, t in seconds, using the function h of t equals negative 5t squared plus 20t plus 2. For this example, we will focus our observation on the time interval from 0 to 4 seconds. Let us break this down step by step. Step 1 is understanding the context. As the ball travels through the air, its height changes over time. Our primary goal here is to determine the highest point the ball reaches during its flight. In step 2, we identify the maximum. By analyzing the function or looking at its graph, we find that at exactly 2 seconds, the height is calculated as follows. h of 2 equals negative 5 times 2 squared, plus 20 times 2, plus 2. This simplifies to negative 20 plus 40 plus 2, giving us a height of 22 meters. If we were to check any other time between 0 and 4 seconds, we would find that the height is always less than 22 meters. Step 3 is where we apply the formal definitions we discussed in the previous slides. Since the height at 2 seconds is greater than the height at any other time in our interval, we can formally state that the maximum value is 22 meters. It is important to note that the point of maximum value is t equals 2 seconds. Finally, in step 4, we identify the minimum. If we check the start and end of our interval, we see that at 0 seconds, the height h of 0 is 2 meters. Similarly, at 4 seconds, the height h of 4 is negative 5 times 16, plus 80, plus 2, which also equals 2 meters. Since 2 meters is the lowest height reached during this specific time frame, the minimum value is 2 meters, and the points of minimum value are t equals 0 and t equals 4 seconds. Pay close attention to how we distinguished between the value and the point in this example, as this is a critical distinction that we will explore in the next slide to avoid common mistakes. Common mistakes to avoid. Now that we have seen how these definitions apply to a real-world scenario with our projectile motion example, let's discuss some common pitfalls. It is very easy to make small conceptual errors here, so please pay close attention to these 3 points. First, a very frequent mistake is confusing the point with the value. It is vital to remember that the point refers to the input, or the x-coordinate, while the value refers to the output, or the y-coordinate. For example, it is mathematically incorrect to say, the maximum value is x equals 2. Instead, the correct way to state this is, the point of maximum value is x equals 2, and the maximum value is f of 2. If you recall our ball example from the previous slide, 2 seconds was the point, but 22 meters was the actual maximum value. Second, you must be careful not to ignore the interval, which we have denoted as capital I. A function might have a maximum within one specific range, but if we change the boundaries of that interval, the maximum could change or disappear entirely. Therefore, always check the given domain or interval before you declare a value as the absolute maximum or minimum. Finally, do not assume that every point where a graph turns or changes direction is necessarily an extreme point for the entire interval. While a point might look like a peak or a valley in its immediate neighborhood, it may not be the highest or lowest point of the function across the whole interval. These are known as local extremes, and we will study those in much more detail in the subsequent subsections of this chapter. Keeping these distinctions in mind will ensure your calculations are precise as we move toward our final summary. Key takeaways. All right, to wrap up this introductory session, let's summarize the key takeaways to ensure everything is clear before we move on to the actual calculus techniques in the next lesson. First, let's recap the maximum value. This is the highest output of the function, which we call f of c, provided that f of c is greater than f of x for every other x value within our specified interval. Similarly, the minimum value is the lowest output, f of c, where f of c is less than f of x for all other x values in that same interval. As we discussed in the earlier slides, the term extreme value serves as a general collective name for either a maximum or a minimum. And finally, the extreme point is the specific input value, C, where that extreme value occurs. Just keep in mind the distinction we highlighted in the previous slide. The point is the where on the x-axis, while the value is the what on the y-axis.